Okay, hello, welcome back to another one of my recording sessions where I talk about genetic algorithms and very basic stuff, and talk about what I did or what I've learned, what I think I should do or could do or shouldn't do, etc. So in this session I'm going to cover this notebook, this one right here, and this is almost the same as the last notebook, Jupyter notebook used, and therefore the recording session shouldn't be too long. It will be shorter, I think, but we'll see. And the main I think the main purpose of this notebook is to get more entities with better scores, with better sum utility values. Because last time, if I remember correctly, I ran the evolution script, evolution cell, for about 6-7 times, and I did not get numbers that I thought would be satisfactory. So in this video log, I'll do that, since I know the answer, since I know how to, one of the ways of doing that, and since I know the answer to this problem set, I'll do that, and also demonstrate the kind of the logic behind it. Yeah. So starting from the very top, this is the same, except this time I've just made implemented some things that I could use to just time the code or the code execution. And it is also important to note that all this time I've had the... Did I? Or did I not? I don't know. Well, in this example, in this notebook, I am actually going to have the genesis pool, the genesis or the initial population pool kind of fixed to kind of reduce the randomness, but the work I've done actually shows that it does not really affect the outcome of the evolution in any bad way, or in the research techniques or methods that are used. So for now, for this Jupyter notebook file, I'm going to fix it. I'm going to just set it as a fixed initial population, and all the items list are the same, all the values are the same, all the constraints are the same, and all the functions are also the same. Although since the genesis 0 is fixed, I won't be using the random gene generator. But other than that, I'll be using most of the things here. So the max constraint is 4000, and the population size is 500. Number of items 20, genome length 20, same as the number of items. Mutation rate is 0.03, as in 3%. Crossover rate 0.7. I don't know if I'm using that right now. Maybe not. I don't know. Let me just check. Nope, I don't think so. Nope, I don't think so. Anyway, and initiate genesis and play. So I'm just gonna run everything. We see that best entity so far from the fixed genesis is 730, and it probably has a weight of 4840. so that is above the weight threshold, so that's not good. So run that. Should I run it? I don't know. How long does this take? Seriously? Seriously, how long does it take? Hello? 98 seconds. Fine, I'll run it. Why not? Really? I didn't? Shit. So I can see the progress here. It should take. Oh yeah, it's also important to note that during this evolution process, that is 3,000 generations long, although it starts with 500 entities, the max population is 700. So that is because sometimes too many entities just get removed and the same amount gets added, and sometimes there will be duplicates, so there's the additional 200 entities can be thought as redundancies, but not in a bad way, in a good way, as backups. And it would create, or rather allow, higher diversity, if that makes sense. And hopefully the goal here, or the result, gives us entities as close to 710 as possible. So maybe 700, because last time I did get 700. Yeah, 92 seconds. So that was okay. That was decent. This time I got 695, which is good compared to 660s and 650s. But this is still lower than 710 or 700, which I got last time. And these are the outcomes, the entities. Yeah. So what the difference here is that where is it? The difference here from the previous notebook is in the weight of things being chosen, not chosen. So if you just run this, this will give us let's just. So this starts from 500. These are the weights of every element. These are the weights of every element in the list of entities. Yeah. So higher this number, the more likely it is that the entity in that corresponding order of the list gets chosen. So the first one, being 500, means that it's the top entity, the entity with the top summed utility value is most likely to be picked. And the next one is 166.6666. Yeah, is that. So what I'm trying to do here is divide the population 500, divide the number of population, which is 500, and which is 500 by what did I do? By 1, 3, 5, 7, 9, 11, 13, 15, 17, 19, etc. Whereas in the previous in the previous script, in the previous notebook, this is what happened. See here, the weights don't vary that much as the order goes proceeds. The entity with the highest summed utility value has a score of 1000. The next one 99999. The next one is 998, 997. So it decreases by 1. So this way, the top the top one, the first one, is not that much more likely to be picked as one of the parents compared to the second one or the third one, or all the way down to the 100th one, which is why in the previous notebook it wasn't likely that at the end there were going to be entities scoring higher than 650, because the top ones didn't get rewarded enough, and thus not that many very good entities were born. But again, that's that. But what I'm about to say from right now is also in hindsight now, and I will be covering this in future videos. But what happens, or what I should consider, is that I have done some things where I did make sure that the higher scores got rewarded a lot more. However, that led to also not always the best entities. The best entities used to exist, but they die out. So, and I think that's also that may be because of this of my mistake in setting the algorithm for adjusting the weights, so that the weights favor high scoring entities. But if there are more genes, if the genome length is longer, that really doesn't work all the time. Yeah. So there has to be a way to counteract that, etc. Maybe the lone island procreation function or parent selection function that I created, but I still have to test those out anyway. But so far, at this stage, favoring the entities with higher summed utility values does seem to do a better job. But then again, that's also that, full stop there. Another idea to consider is that I always have to consider is what is good or bad, what is just normal, or just neutral, or really really bad, or really really good, or just best or worst, or near best or near worst, because these things change. And for simple or simpler problems, that's okay, but for harder or more complicated problems where I would need some diversity in order to prepare for, or in order to increase the robustness of the entire population, diversity is needed. I would need to find a way to guarantee that kind of diversity. It could be a combination of parental selection schemes. It could be an increase in the population. It could be the mutation rate, an adjustment in the mutation rate, etc. So that's about it. That is still a lot shorter than my last video. So, oops. Thank you for watching, and goodbye. Peace.